guess others did not like the cold this morning either. Where is everybody? Alright, well, it's time. We'll get started. I was looking at the schedule and I made a mistake. The exam isn't scheduled until Wednesday, not Monday, so.
What's that?
The exam is scheduled for Wednesday, not Monday.
Oh, good.
For some reason I had it in my head that it was scheduled for Monday. Today I want to get through three things. I want to cover chi-square tests of homogeneity. We've done chi-square tests of independence, and we've done chi-square tests of goodness of fit. And so I want to show you homogeneity. I also want to introduce you to an alternative to the chi-square test, which is called the t-test. It's in your homework assignment, and so you haven't been able to do that homework question necessarily until we've covered it in class. And then the last thing I want to do today is take you through an example of a Shapiro-Wilk test, which is a test of word normality. That is also in your homework. So after we've done that, you should be able to then accomplish that task. But I stapled them together. I have some handouts for you that I evidently left in my office. I'll be right back.
The exam is on Wednesday.
Oh,
Yeah, it's a little extra. Exams on Wednesday, that's what exam is on Wednesday. That's a good thing. That's a good thing. Come on. It's better than Monday.
Are you going to have?
Okay, peace and we'll be back. Peace and we'll be back.
I leave and no one's here, and I come back and everybody's here. Pass this down. So those. What I'm giving you are photocopies from a book of statistical tables that are a chi-square distribution table. So it shows you what the distribution is. It also gives you the critical values that are associated with different p-values. You see that the figure on the front of this shows you a chi-square distribution that has a shaded region. You see that that shaded region starts at about 3. That's just an example, but if you were looking at 1 degree of freedom at an alpha level of 0.05, that shaded area should start over here at about 3.8. And so it's showing you where on the chi-square scale, from a chi-square of 0, which is hardly any difference at all, to more and more extreme values of chi-square, how much of the area is under that distribution. The lower alpha is, the smaller that area at the tail is going to be under that curve. So this shaded area shrinks and expands depending on how you have set your alpha level. And when you set your alpha level, it will tell you in the table that is on the back side, it will tell you for a given alpha level and a given degree of freedom, what is the chi-square value that you need to be higher than in order to conclude that two things are different, two distributions are different, or that things are significantly non-independent or non-homogeneous. So you have that. The other thing that we have is the Shapiro-Wilk test table. There is kind of a complicated formula that you will find over on the second to the last page of this thing. I'll introduce you to the Shapiro-Wilk equation. But in this equation, there's a variable A, and you get A from this series of complicated tables. These tables have been worked out by statisticians. Your tables go up to a sample size of 50. The example in your homework is for a sample size of 50, so you'll be using this last column, and we'll get to that when we go through your test later on. So you should have everything now that you need to have in your possession to do the homework assignment once we run through a chi-square test of homogeneity. Now, when we talk about chi-square tests, remember that I told you that you can think of chi-square tests that are intrinsic to the data or extrinsic to the data. Intrinsic to the data basically means that the data themselves dictate what the expected values are. This is typically going to be a chi-square test with independence. Spell. Extrinsic to the data means that there's some distribution out there that is dictating what the expectations should be. And so, and this is generally what we see when we see a goodness of fit test or a chi-square test of homogeneity. In these cases, you're not using things like row and column totals to dictate what the expected values are. Typically, you're using some external distributions to tell you what the proportion should be, and that's where you get your expected values. So the nice thing about doing this on even years is that sometimes we teach this class during an electoral year when we vote for president. And so the example in your homework is actually from the 2016 election. This example here is from the Iowa caucuses. So these are supposedly the votes that were the initial preliminary votes that came out of the Iowa caucuses for Democratic presidential hopefuls, and it showed that Pete Buttigieg and Bernie Sanders got 564 and 562 votes apiece. Elizabeth Warren got 388, Joe Biden got 340, et cetera, et cetera. Poor Andrew Yang, who's now no longer in the race, got 22, and Tom Steyer got 7. And so one of the questions that you could have is, a question that most people have, like, who won the Iowa caucus? Another way of saying that is, did the voters in Iowa have a preference for a particular candidate? In this case, what you're basically asking is, are these different proportions of voters, are they similar to one another or are they different? And so this is what a homogeneity test is. Is 564 votes and or 562 votes really different from 22 or 7 votes? And as somebody said last time, well, course, they're different. Some of them are in the 500s, and others of them are in low double digits or single digits. But we can put a number on that conclusion that yes, Iowa voters have a preference. And so what we do is if we treat this as the observed, there were 2,147 votes cast. And that seems like a small number of votes in Iowa, but because the caucus is a weird arcane political system by which people determine which delegates get chosen, it ends up being a relatively small number. So what we would expect then, if everybody got an equal share of the total number of votes there, you would expect each of these individuals to have gotten 306.71. So these expected values are extrinsic to the data in that we're assuming homogeneity as our null hypothesis. Everybody got the same amount of votes, and we're comparing the observed to that. Yes, Athos?
Are we just working with null hypothesis to calculate the expected values?
You're always working with the null hypothesis. There's always a null hypothesis out there if you choose to think in those terms. In this case, the null hypothesis is evenness.
Yes.
In a case of independence, the null hypothesis is that the categories that you're looking at are independent. If you are working with a goodness of fit test, your null hypothesis is that one distribution matches the other distribution. Those are all null hypotheses. And then you're testing to see whether or not that's true, at least reasonably true, given the data you have. Grace?
So for test of homogeneity, your expected values will all be the same.
They will all be the same.
Okay.
Because that's what you're testing. Are these numbers different enough from what you would expect if there was no preference?
Okay.
So if there was no preference, if Iowa voters just really didn't care who they send on to compete in the presidential race, then there would be no difference between any of the candidates, obviously. But Iowa voters clearly do care because they chose a couple of candidates over the rest of the candidates, and the last two candidates they didn't care for at all for whatever reason. So this is a question of preference in this case. So a chi-square test of homogeneity is just like a chi-square test of any other type. We take the observed minus the expected, we square that, we divide it by the expected, and we sum that up across all the different categories. And in this case, we have 1, 2, 3, 4, 5, 6, 7. We have 7 candidates. And you might say, well, Paul, there can't be only 7 candidates because there are like 14 Democrats running for the Democratic nomination, but the remainder of the list didn't actually get any delegates, and so they don't appear in this group. They appear in a category called Other that got 0, so I'm just dealing with people who actually came out of Iowa with something in their tally. And so if we do this for the observed versus the expected, you see that there are big differences here, not much difference here. Elizabeth Warren and Joe Biden and Amy Klobuchar got about what you would expect in terms of the expectation if everybody got the same amount. And then Andrew Yang and Tom Steyer were definitely on the short end of the stick. And so you can look at the contribution to the overall chi-square statistic, and you can see that some candidates were pretty close to the expectation, other candidates were really far away. These guys got more than their fair share, these guys got way less than their fair share. You can also see from this chi-square statistic as we add up the observed minus expected squared divided by the expected, we see that these numbers are all big, and so you get a monstrously huge chi-square statistic of 1,016.57, and that is a ridiculously large chi-square value. If you go and look in your chi-square table for chi-square statistic at an alpha level of 0.05 and 6 degrees of freedom, what is the chi-square value? What's that? 12.592. 12.592. Well, your observed value of 1016.57 is way, 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 way bigger than 12.592. And so you would conclude what about the Iowa voters? They expressed a preference. These delegates are not evenly distributed across the candidates because people preferred 2 or 3 of the candidates over these 2 candidates, and that's what's driving this gigantic chi-square statistic. It's all being driven by these 2 candidates and these 2 candidates for the most part. So looking at these things tells you which parts of the chi-square are probably driving the overall chi-square value. You could then partition this up. You could say, well, is this primarily due to differences between Buttigieg and Sanders versus Yang and Stiers? Omit Warren, Biden, and Klobuchar. Say these are the middle moderate sort of people. Say, is it these 2 extremes that is driving the chi-square? Reconfigure how many total delegates you're talking about, recalculate the chi-square, and you're going to find that, once again, it's that big gulf that is driving the chi-square statistic. You could also divide it up and put Buttigieg, Sanders, Warren, Biden, and Klobuchar in here and exclude these guys, and what you're going to find is that the overall chi-square test is still going to be significant, but the magnitude of the chi-square value is going to be much smaller because you've removed this big difference from this big difference. So in that case, you're going to reduce this number by just a little bit, but you're now going to be dividing it by 5 candidates rather than 7 candidates, which means that this is all going to go up a little bit, which means that these numbers will come down, these numbers will go up slightly, but you still won't have anything like the chi-square value that you have with all 7 of them in there. And by decomposing, by what we call partitioning the chi-square in this way, we can actually test, well, what exactly is responsible for this gigantic, humongous chi-square when everybody is in there? Is it actually the contrast between Buttigieg, Sanders, and Yang and Steyer, or is it the contrast between Buttigieg and Sanders and this suite of 3 candidates, third, fourth, and fifth? And what you're going to find when you do that, if you choose to do that, is you're going to find that most of the chi-square is being driven by the contrast between Buttigieg and Sanders and Yang and Steyer. It would I haven't done it yet, but my guess is it would still be significant when you include all 5 of the top 5 candidates, but it's going to be a way lower level of significance as a result of that. So you can do these kinds of tests on a full data set, but then you can also go after that and partition it in order to try and identify what specifically is driving the original significant result. And this is referred to as partitioning. The chi-square. You now take subsets of it in a search for figuring out what in that. All this tells you, all this test that we've done tells you is that something's different. In order to figure out what exactly is different, you have to look at that whole thing more carefully. Okay? You have primary results from the 2016 election, I think is what I put in there, that do the same thing. You would want to test that with a chi-square test of homogeneity. Now, here's the tricky part, is deciding when you're doing a chi-square test of homogeneity versus when you're doing a chi-square test of independence versus when you're doing a chi-square test of goodness of fit. The answer to all those questions depends upon what the question is that's being asked. The question here was, did voters in Iowa have a preference? Well, if there's no preference, that means everybody gets the same number of delegates. That's a homogeneity test. If the question is there a relationship between income and your recency of a visit to the emergency room, that question deals with how is this method of classification related to this other method of classification. That is a chi-square test of independence. If we are asking, does the current distribution that we're looking at match up with some other distribution. Maybe it's a normal distribution, maybe it's a distribution dictated by some other extrinsic expectation, then that is a goodness of fit test. So the chi-square test, which kind of chi-square test you apply depends upon the question that's being asked of the data that you have. And so sometimes figuring that out is pretty simple and straightforward, sometimes figuring that out is a little more complicated and obscure. So always be sure that you understand what the question is being asked of the data that you have in front of you. If you get that wrong, you're going to apply the wrong method. And while you may get the right chi-square statistic, because chi-square statistics are very similar in how they are calculated, you won't necessarily interpret that statistic correctly because you didn't understand what the question was that was being asked. So, questions about chi-square? Okay, let's analyze the same data using a G statistic. The G statistic essentially does the same thing that a chi-square statistic does. The nice thing about it is that you can do a G test on data that you're looking at for homogeneity, goodness of fit, and independence, but the way that you calculate it is different. G for a homogeneity test is 2 times the observed value times the natural log of the observed divided by the expected value. There's no squaring or anything else. It's just the observed times the natural log of this multiplied times 2 when this is summed up across all of your categories. So in this case, we would basically just take the observed times the natural log of this divided by that and multiply those things together. That would give you 343, et cetera, et cetera, et cetera. You see the same kind of pattern here, except that in this case, one of the things that the G-test does that the chi-square doesn't is it weights uncommon observations less than common observations. So this is one of the biases of the test. And so it looks like Andrew Yang and Tom Steyer are going to contribute less to the overall G-test than these 2 candidates that have a lot of delegates. And so it would just be 2 times, in this case, 564 times the natural log of 564 divided by 306, and plus 562 times the natural log of 562 divided by 306.7, et cetera, plus 388 times the natural log of 388 divided by 306.7, et cetera, et cetera, and so you get down to Tom Steyer, which would be 7 times the natural log of 7 divided by 306. And so you would add all that up and then multiply that times 2, and what you should get at the end of that is 1372. Now, one of the things that you'll notice about this is 1372, so the G statistic for this, 1372.23608. You, once again, would look this up in the chi-square table for 0.05 for your alpha level, and your degrees of freedom will equal 6. So it's still going to be compared to 12.59, and so it looks even more extremely different than even the chi-square test did. So you get a different result, but for any given data set, if you do it with a chi-square test or you do it with a G-test, it should give you the same qualitative results, even if it doesn't give you an exact quantitative result. Yeah.
Where did you get the 303.7? Yeah, 562 natural log over 562. Should that be 306?
It's the observed times the natural log of the observed divided by expected.
Oh, okay.
Yeah, so the expected is always in the numerator, is in the denominator. The numerator is the observed So it's just another way of doing the same thing. You could do this with any of the tests. The calculation differs when you do a chi-square, a g-test of independence. Just like when you do a chi-square test of independence, the equation is different. In that case, it's a little more complicated. It's still based on this whole thing here. But for a chi-square test of independence, let's go back to the emergency room visit data. For a chi-square test of independence, what you would do is you would divide up this table into different components. One component would be the component of your actual data. And the actual data would be, you would apply this structure to it, this equation to it, where you have the observed times the natural log of the observed over the expected. And in this case, you would calculate the expected the same way you do it in a chi-square test of independence. It's the row total times the column total divided by the grand total. So you would still calculate the expected values the same way, but rather than doing observed minus expected squared divided by expected, you would do observed times the natural log of observed divided by expected. And you would sum that for all of the data. Yeah.
So why do we have to multiply by 2 for the homogeneity?
Just the way the test is built.
Okay.
But we're not finished here. There's a second equation here where you're going to now take doing this right? Am I doing this right? Yeah.
What if we get a value of chi-square that is way bigger than the table?
It means that there's something different there, like way different. If it's bigger than any value in the entire table,
No, like a little bit bigger.
a little bit bigger is still different. What's your conclusion is that it's either independent, it's either not independent, or it's either not homogeneous, or it either doesn't fit two distributions or not fit. Skip this. I think I'm confusing my equations because the columns don't have an expected value. Skip g-test for independence because I think I've confused the equations in my mind at the moment. Too many equations floating around. Yeah, skip it for independence. I won't ask you that on the exam. because there's a limited amount of time. Anyway, the equation is slightly different, and the reason that I'm having trouble figuring this out is that one of the aspects of it is you use the column and row totals, and there isn't an expected value for the column and row totals, and so it can't be that equation, and I'm just having trouble dredging it up in my mind, which one it is. Okay, questions about tests of homogeneity, tests of independence, tests of giveness of fit using chi-square. If you're still struggling with what type 1 error rate and type 2 error rate and things like that are, come by and see me in my office, and I'll try and figure out another way of talking to you about it. But hopefully we've solved most of those questions. All right. The last thing is a test of normality. So, assuming that you have a population, a statistical population out there that you are interested in, this population can have a variety of different forms. If you're measuring things like the heights of humans, you're going to see that that has a normal distribution. If you're measuring the lengths of the body lengths of a bug, like the femur of aphids, you're going to see that that probably has a normal distribution. But there are plenty of distributions out there that you're going to find are not normally distributed. So if we're looking at beaks of finches in the Galapagos, where they're undergoing a type of selection that's driving two populations apart, you might expect a bimodal distribution in your original population. If you are counting things, so for example, let's say that you are counting the number of times people use their credit card per month. What you're going to find with count data is that they tend to have a distribution such that there are usually more observations at lower counts, and there are fewer observations at higher counts. This is sometimes referred to as a log normal distribution, and it's not normal. These extreme values tend to drag the mean of the value, the mean of the distribution up. So the population mean is here, the median is somewhere right here, and the mode is obviously right here, the most frequent observation. So what does the central limit theorem tell us about these three different kinds of distributions? This will be on the test on Wednesday. What does the central limit theorem tell us about these three distributions?
If you take samples from them, the means of the samples graph out to be a normal.
If you take samples of a given size from these populations, do that 10,000 times, graph those sample means will have a normal curve. What's one of the assumptions of this in terms of sample size? How big does your sample size need to be? It does matter. 30. It needs to be around 30. 30 is kind of the magic number. So what happens when you have samples below 30? Which plenty of people do, trust me. I see it all the time in biology. Students presenting data with a sample size of 1 or 2 or 3 rather than 20 or 30. What happens is you need to have a sufficiently large sample size for the central limit theorem to be applied. And so the reason that people expect you to test the normality of data at the beginning of a statistical analysis is because oftentimes people have small sample sizes. And a small sample size is less than 30, according to the central limit theorem. So in this case, what people want you to do is they want you to test the normality of your data, because if your population is normal, any given sample, even small samples, will generally have a kind of normal shape to them. And then, if that sample is normal, then certainly the distribution of sample means will be normal. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we have a sample size of 10. So the reason that people want you to test normality at the beginning of an analysis is that if you're dealing with small sample sizes, if you begin with a population that is normal, you will tend to get samples that are normal, and that will automatically mean that the distribution of sample means is normal. And so the whole reason for doing these normality tests is to reassure people that we can assume that the distribution of population, but the distribution of sample means is normal. Now, we showed you numerically that even at relatively low sample sizes, the distribution of sample means is normal. We did this with the coin flip data. We did this with the simulation in R, where we actually sampled from normal distributions, exponential distributions, uniform distributions, and even at relatively low sample sizes, if you resample that population over and over again, the distribution is normal. What influences what the sample size influences is at really high sample sizes, the normal distribution is nice and tight and peaky, and as your sample size goes down, this distribution tends to spread out. So this might be an N of 30, this might be an N of 10, this might be an N of 5. And so what happens as you have smaller and smaller samples, this normal distribution flattens out, spreads out, and so your confidence intervals around the mean get really, really big, but the central limit theorem still generally holds. So because people expect you to test your data set for normality at low sample sizes, and we're going to show you how to do that. We use the Shapiro-Wilk test because of 7 decades of testing. 7 decades? No. 5+ decades of testing have shown that the Shapiro-Wilk test has greater power than any of the other methods. So we're just going to dispense with all of the other methods. So you calculate Shapiro-Wilks using this, this equation. It's the sum of some coefficient multiplied times the observed value divided by the sum of the observed value minus the mean squared. Once again, this is a squared deviation from the mean. This is how we quantify variation. We take how does the individual data point vary from the mean and square it. That gives us a raw measure of overall variance. So this sums of squares thing that I've been talking about, it just pops up over and over and over again in statistics. So then the question is, where do you get this table of coefficients? So I have a data set. I don't even remember what these data are. It doesn't really matter what the data are. But you basically have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You have 16 data points. And so what you do is you go to the Shapiro-Wilk table that I gave you, and you find in the coefficients of A for Shapiro-Wilk, you find the column 16 here should begin with 0.5056. And what you want to do first is you want to place these data in rank order. So you're going to rank them from 1 to 16, and you're going to rank them from lowest value to smallest value. You see that they're not ranked now because 109 appears here, 104 appears here, 112, 114. And so you just reorder your data, simple ranking. You can do this in a spreadsheet easily. So now they go from 104, 109, 112, 114, 116 to 118s, 119, 121, 23, 25, 26, 26, 28, 28, 28. And then what you do is you go to the Shapiro-Wilk test and you find this column and you copy this column and you place it next to the data starting at the top here. Oh, why did it reveal all of that at once? So you go from 0.506 through 0.3295, et cetera, until you get down to the middle here. The first half gets all negatives, the second half gets all positives. And so all you did was you took this column, copied it from 0.5056 down to 0.0196, put it there, put negatives in front of it, put it here, put positives in front of it, and now you can take the value, multiply it times the coefficient to get the numerator values for the equation.
So that's a mirror image thing going on?
It's a mirror
in
image
that
thing, yep.
column?
Yep. 0.0196, 0.0594, 0.1007, 1448, 1939, 2514, 3295, 5056. The lower half of the data set, the smaller half of the data set gets negative values. The other part of the data set gets positive values. You then multiply the value times the coefficient to get this, value times the coefficient to get this. This whole thing added up adds up to 741, and that is your numerator. So in this case, W is the sum of the coefficients times the value squared. So these things are this times that squared. Wait, no, this is this times that. Half of 104 is 52, but then we square each of these things and add them up, and it will add up to, sorry. Add all of them up and then square the final result, my bad. Add all these up, the sum is 27.232, the square of 27.232 should be 741.647. So where the parentheses are here actually matters. You take the sum of all of those coefficients times the values, and it's that sum that you square. You don't square the individual values. If you square the individual values, you may get something different.
So in our equation, we need to have the square on the top, not on the bottom.
The square is on the top. There is also a square on the bottom, but the square is relative to the things inside of the parentheses. You'll get a different answer, a very different answer, if you put the parentheses in here.
So at the bottom of that column, it's the square of the sums, not the sum of the square.
Yes, it's the square of the sums, not the sum of the squares, so that is exactly
And that's
what it is.
all that is where that lead parenthesis goes.
Yep. If you put the parentheses in the wrong place, you will square each of these things instead. These will all turn positive, and then this number will be really huge, but it won't be nearly as huge as this number because ultimately this number is the sum of all of this squared. So where the parentheses are matters. And then the numerator is the sum of the square deviations from the mean. Deviation from the mean squared, summed up across all of them. This is basically just accomplished by finding the average value, subtracting the mean from that value, squaring it, mean from this value, squaring it, mean from that value, squaring it, and then adding all those up, and that gives you 799. And so in this case, 741 would be divided by 799, so your Shapiro-Wilk statistic is 0.9277. 0.9277 for 16 values in your data set. Then what you have to do is you have to go and This is crucially important, which is why I've underlined it in red. The null hypothesis of normality is rejected if the observed value of W is less than or equal to the tabled critical value for the given sample size. So two things that are important. Significance is achieved, meaning that you have a non-normal distribution, if the calculated value of W is less than the tabled value of W for the sample size, not the degrees of freedom. So we don't subtract one from the sample size. And so when we go to the critical values, we would go to, notice how it has N here, not degrees of freedom. So sample size of 16 and an alpha level of 0.05 gives you a value of 0.887. The observed value is larger than the table value,
So there's no,
and so these data are not significantly different from normal. Okay? But it's critically important that you reverse your thinking, because with all our chi-square tests and everything, we were looking for a chi-square value that was bigger than the table value. With the Shapiro-Wilk test, we're looking for a value that is smaller than the table value for significance. So
and the null hypothesis is that it is
normal.
normal.
The alternative is that it differs from normality in some way. So on your handout that I gave you, you might want to just underline this section for your own reference, so that when you go back to it, you're like, okay, I need to remember to follow this instruction carefully after.
Okay, what if we got like 35 there?
If we got 35 here,
Yeah, it's still bigger than.
it's still bigger than that, it just means that it's not different from normal. Doesn't change this. Once again, the table value is a line that you're crossing.
It's whether yes or no, right?
And so you only say things are not normal if this value is lower than the table value, not higher than the table value. So it doesn't matter how much higher than the table value it is. And when you think about this, where is the variation happening?
Down in the denominator.
Yeah, so as variance increases, as your deviance of the individual data values from the mean gets bigger and bigger and bigger, what happens to that distribution of your data? It's getting wider and wider and wider, sloppier and sloppier. As a result, as this thing gets large, this whole thing gets small. And if you have, remember, a normal distribution takes on a particular form for a particular sample size. I also talked to you about skew and kurtosis. What was skew?
Table to the side.
Skew can either be positive skew or it can be negative skew, where you have a tail that goes out towards one of the sides. So that's what skew is. What is kurtosis?
The peak, how high, how tall is the peak?
Is it squunched in and peaky, or is it really flat? Now, for a given sample size, a normal curve will have the normal shape, but it will also have a certain amount of variance around the population mean. And that is set for a normal distribution. It has not only a mode that is centered on the population mean, but also the variance around that mean and mode are set. There's an expectation of what that distribution will be at a given sample size. So let's say that this is a distribution of a population of 10,000 individuals. As you increase that, the population basically gets narrower and narrower and peakier, but it still falls within these expectations. As you get fewer and fewer data points, that distribution tends to spread out. And we know what that distribution looks like because theoretical statisticians have figured out the shape of the normal curve. But within a sample size of a given sample size, let's say you have a sample size of 100, within that, this population can be more squunched or more peaky. That's kurtosis, the degree to which it looks like a normal curve, except that the peak is lower than it should be, or it's taller than it should be. The number of observations that go into making the mode are either more common than they should be, or they're less common than they should be. That's kurtosis. So kurtosis occurs when you have either this or this that is wrong for your particular size of your population. So you can differ from normality in kurtosis. So you can have something that looks normal but isn't normal because it's either too peaked or too flattened. If you flatten this out, this number gets bigger and bigger, which then reduces this whole thing, and you get away from normality because your variance was too big. And so that's a common deviation from normality. You also get more deviation from normality when you have a skewed distribution because the mean gets pulled up because of these extreme values, which means that the mean is now further from the bulk of your distribution, which then drives up your denominator in this case. So the types of deviations that you see from normality, skewness and kurtosis, these things tend to make the denominator bigger, which makes overall W smaller. So you're looking for a small calculated Shapiro-Wilk statistic to determine a deviation from normality. And it has everything to do with what's going on with variance, as variance is influenced by skew in the data or kurtosis in the data. The ultimate kurtotic distribution is this, right? This is a uniform distribution. Uniform distributions are patently non-normal because they're uniform. So this would, once again, have a very high denominator because in a normal curve, most of the values are clustered around the mean. Here, they're uniformly distributed across the range of x values, and so they're not clustered around the mean at all, and so you're going to have, once again, a larger variance estimate, and as a result, a larger sum to squares estimate, and as a result of that larger sum to square estimate, the W statistic, the Shapiro-Wilk statistic, is going to get smaller and smaller. Yeah.
Can you go back to your slide where you did the calculations?
Yeah.
I just want to look at it. You.
Yeah.
How did you get the calculations for the last column?
Sums of squares, it's just, sums of squares is always the deviation of the individual data points from the mean squared. So this value is 104 minus 119 squared. 109 minus 119 squared. You're looking at me like you don't believe that, Connor.
I got you now.
104 minus 119.6875 squared, that's about 15. 15 squared is 5, 2, 7, 15. Sorry. Helps if you can do math. 5, 12, about 225. So because I rounded, it's not quite that, but doing quick calculations in your head, you're dropping the decimal points and stuff like that, it'll give you an idea of whether or not the thing that you're actually calculating is in the right ballpark. 109 minus 119 is 10. 10 squared is 100. So they're all in the ballpark. The deviation is because of the decimals that we're not calculating yet. So it's simply the individual values minus the mean squared, and then sum that whole thing up. That's what goes in the denominator. So one of the things that you should get used to seeing is the sum of the squared deviations from the mean.
Say that again.
One of the things that you should get used to seeing constantly is the sum of the squared deviations from the mean.
That's the
Denominator
result,
in this case.
that's the result, that's the 799 at the bottom of the last column.
Yep. Remember to calculate the sample variance. What do? We sum the squared deviations of the mean and we divide by that by the degrees of freedom. Sum of squared deviations from the mean divided by the degrees of freedom. That's what sample variance is. In this case, once again, the sums of the squared deviations from the mean appear in the denominator. It's the way in which we calculate a measure of variability. Why do we square it?
So you don't have negative values, right?
So to get rid of the negative values. If you don't square it, the negative and positive values will cancel out when you add them all up, and they'll just sum to 0. And so you square each of the individual values before you sum them, so you can get an aggregate view of how the data are varying from the mean in this case. Yes, Atlas?
The second x in the top part of the equation is the mean.
This is the mean. This is the sample mean. This book uses y instead of x because your y is usually the response variable, but it doesn't matter. It still means the same thing. It's the individual sample values minus the mean squared, and then summed up. This is always abbreviated sums of squares. When we get to ANOVA, you're going to see that this is the numerator in a calculation in an ANOVA table. So we're going to revisit some of the squares over and over and over again in here. Questions? Yeah.
Are we having an exam Wednesday?
Exam on Wednesday, yes.
Do you do study guides?
I don't typically do study guides. I will tell you that what is going to be on the test is some questions about theory, about sampling theory, about central limit theorem, about confidence intervals and what they mean, about type 1 and type 2 error. And then the rest of the test is going to be working problems. And so because problems are time consuming to work, you can expect problems to be relatively small in size, and that they're not, I'm not going to give you a sample size of 50 to do a Shapiro-Wilk test on, because that would take too long, as you're gonna find as you apply Shapiro-Wilk test. But what I've done is on the homework assignment, on the problem set, I've given you a Shapiro-Wilk test of 50 observations, the maximum that the table has in your book. There are Shapiro-Wilk tables that go up to 2,000 observations. We're not gonna do those. But this will give you enough practice with a big data set for Shapiro-Wilk tests so that should you see a Shapiro-Wilk question on the test, you should be able to work through it if it's a data set of 10 Shapiro-Wilk.
Okay. So we have chi-square test, the G one.
Chi-square test, G-test, of homogeneity,
Shapiro.
chi-square test of homogeneity, goodness of fit, and independence. So you should expect to see each of those things on there. I'll have copies of the chi-square table printed on the exam. I'll have copies of the necessary Shapiro-Wilk coefficients on the exam for you. So bring a calculator and be prepared to work some problems. Yeah.
What types of data be on the test?
Pardon?
What
Oh
types?
yeah, types of data will be on the test, certainly. And yeah, so that whole nominal ordinal.
Whole PowerPoint basically.
Yep. Yeah.
Will you give us the equations for different?
I won't give you some equations, and here's the reason why I won't give you some equations. I'll probably give you Shapiro-Wilk because it's different than the other equations.
Yeah.
What I'm not gonna give you is I'm not gonna give you an equation for the mean, I'm not gonna give you the equation for the variance, I'm not gonna give you the equation for standard deviation or standard error of the mean.
Okay.
Do you use Excel for the exam?
No, I'm gonna give you data sets that are small enough, you should be able to work them out on a calculator. By design, it's going to be data sets that are small enough. Why would I not let you use Excel?
You can just type in the equation.
Click and drag.
You don't even have to type in the equation. If you wanna know what the standard deviation, you just have to say equals STDEV dot S and then the range of the data. Okay, all that tells me is that you know how to operate Excel. It doesn't tell me that you have any idea of what the standard deviation is. Same thing with with variance. var dot S, data range. Why do I want you to know the equation of the variance?
Do you understand what changes it, stuff like that?
This appears over and over and over again in this class. You're gonna get so sick of that equation by the time we're done with all of this. You should know that equation. Because, you shouldn't know that equation. Why do I know the equation?
Maybe it's my times.
Oh my God, I've used it so many times. But more particularly, I know the equation because I know what variance is. And because I know what variance is, I have an ingrained idea of what variance is, and that leads me to the equation. Think of this equation this way. Better to know what to do and then derive the equation from knowing what to do than to know the equation and try and figure out what to do from the equation. Because people write equations different ways. I could have easily written this equation, W equals the sum of A times the x values squared divided by the sum of x values minus the mean squared. That's the same equation, I'm just calling the variable x rather than calling the variable y. Equations screw you up because people don't really understand the language of equations. But if I have an x number line here, and I take a series of observations from this x number line, I can average these up. Where's the average going to appear? Somewhere here in the middle. That's the sample mean. What is variance? Variance is how spread out are the data around the sample mean. Well, how can I put a number on that? Well, I could ask myself, how does the mean differ from x5? How does the mean differ from x3? How does the mean differ from x7? How does the mean differ from x4 and x2? How does the mean differ from x6? How does the mean differ from x1? But the problem with that is if I do the value minus the mean, over here, this is going to be negative value, negative value, negative value, negative value. These are all going to be positive values. And if I add all of those up, what is it going to sum to? 0. It's going to sum to 0 because the mean is right in the middle of the data set. By definition, that's how we calculated the mean. So if I sum all of those up, without squaring them, it's going to sum to 0, which then tells me nothing about variation around the mean. So how can I get around that?
Standard deviation.
Square them. Then that gives me an actual positive number, and then I divide it by the degrees of freedom. Why the degrees of freedom rather than the sample size? Because I had to use one estimate in order to calculate variance. You know the equation for variance because you know what variance is attempting to quantify. That's how you should approach these things. Tom?
Your S squared, that's variance.
Variance.
The, over on the right side, the SS
Sums of
That's
squares is
different.
just the numerator of the
That's the
variance.
numerator of the variance, okay. And what is SS? What is it?
Sums of squares, it's just shorthand, so we don't have to keep saying the sums of the square deviations from the mean. We just shorthand it sums of squares. When we get to ANOVA, you'll see why this is crucially important. We're not there yet, but we'll get there.
And the problem said, when is that due?
End of the day today, 5 o'clock today.
Really?
And that was on the Moodle. Do you want it end of the day on Monday?
Yes.
Yes.
Okay.
Yes,
The
please.
sooner I get it, the sooner I can look at it and get it back to you and tell you what you did wrong to prepare for the exam.
So Monday.
And then-
It's basically exam prep.
Yeah.
So in terms of a study guide, if you want a study guide, the study guide for solving the problems that are gonna be on the test is the problem set.
Yeah. Do you have solutions for that?
I will after you turn it in. I was going to give it to you at 5 o'clock today. I'll give it to you at 5 o'clock Monday.
Okay, and my next question is more cheesy. Those are big problem those are big data sets.
Oh, no,
And you
everything-
say by hand, show all work.
Yep.
That's a lot of lead and a lot of
That's
eraser
fine.
crumbs.
That's fine.
Okay,
No, I can read your crappy handwriting.
okay,
Yeah, no, that's.
okay, and then.
I want you to work them by hand because I want you to know how they work.
All right.
If you know how they work, you never have to rely on an equation, because when you get on a test and you are asked to do this and you think you can know how to do it because you memorize the equation, you're going to find that you don't know how to actually do it.
Okay, and then there's one, in question 2, there's a cryptic comment, it's a chi-square test, and you say, make any adjustments that are necessary given the sample size.
Don't worry about that. I didn't give you a small
Okay,
sample.
good.
I didn't give you small sample corrections. Maddie, you have a question?
So I was just gonna ask, but you already answered this.
Yeah.
If we're like showing our work, is it okay if we do it in that table format that you did on some?
Sure, you can do that, yep. Yeah, I use tables a lot because it helps me keep things straight as I go through it, so it's just a mental habit that I've gotten into over the years.
Show all work.
That's fine. So, as long as you're clearly directing me through what you're doing so that I can follow it, it doesn't really matter how it's organized as long as I have clues as to where to find things. So there are certain things that I'm gonna be looking for, like calculations of second squares and things like that. As long as I can see clearly where you did that, then that's all that matters.
So like